to another lecture. So this is already lecture number 9. So last time I was talking about Turing machines, and I was talking about formal languages and introducing more or less the decidable languages. And well, as I was talking about this, I should also say that there are several types of languages and types of automata which can detect these languages. If the Turing machines are for decidable languages, which are also called recursive languages, then there are some other types of languages which are actually subsets of these recursive languages. So these subsets can be detected by simpler automata. And the most primitive way of doing this is detecting regular languages. And this can be done by finite automata. Regular languages are languages that are either simply words, or what you can do is you can mark several characters and say that they either appear 0 or 1 time, or 0 or 1 or several times. And usually this is done by using a plus or a multiplication sign in the definition of the language. So these regular languages can be detected by finite automata. And the second step is context-free languages. These are languages that can be defined by certain rules. Like, let's say, the rule A would be to override the, or not to override, but to write small a, small b, small c. So you write a big capital A. Capital A is small a, small b, small c. And then, for example, you can define a rule, capital B, and this would be capital A, and then followed by, for example, small a, small c, or something like this. So in context-free languages, the rules can refer to other rules, as it does in capital B, which refers to capital A. But after referring to another rule, you only have literals. So the thing that is important is that you are not allowed to have literals before the reference to the other rule comes. If you have references before as well, then this is a context-sensitive language. And for context-sensitive languages, you will already need a Turing machine. It is still only a subset, or actually, yes. So it's a subset of recursive languages, but you already need a Turing machine. And for context-free languages, you can also use a push-down automaton. So actually, there was an American linguist, actually he's still alive. He was called Noam Chomsky, and he defined the so-called Chomsky hierarchy. So that was actually his big scientific achievement until he became more involved with politics and commenting, politics, Vietnam War and all of this. But he is famous for this scientific achievement of defining formal languages in the Chomsky hierarchy. So the simplest one is the regular language, then comes the context-free language and the context-sensitive language. And then we have the recursive language. And well, each recursive language is also a semi-decidable language, because recursive languages are languages that at both are semi-decidable, that is recursively enumerable, and also co-recursively enumerable. So co-recursive enumerably, that means that if you have a kind of Turing co-decider that always reaches a rejection state when the word is to be rejected, and that in case the word is to be accepted, sometimes reaches the accepting states, but sometimes it's an endless loop, then this is a co-recursively enumerable language. So the recursive language are actually the intersection set of these two sets. And well, the next one is already general languages. So we know that Turing machines, let's say Turing deciders accept recursive languages or decidable languages, but there is no formalism, at least not to my knowledge, for general languages, and it is not relevant to computer science anyway, because in computer science, all algorithms are a combination of a recursive language and a Turing machine. Well, and this is just a topic of theoretical computer science, which is not really relevant to computer programming, but it is still quite interesting. Maybe you have heard about Kurt Gödel, a famous mathematician and logician, who defined the incompleteness theorems. So these incompleteness theorems are basically about what he called formal systems. But these formal systems are nothing but formal languages. So his first incompleteness theorem was that any formal language could be either consistent or complete, but not both at the same time. And the second incompleteness theorem was that a consistent language could not prove its consistency within itself. So there would have to be another language which proves that a language is consistent. And I wrote an essay about Gödel's incompleteness theorems, trying to make them easy to understand using the theory of formal languages. So basically, the first theorem is if you have statements that imply that themselves are wrong, that they imply the negation. Then, for example, in classical logic, if you have a statement, a true statement that implies a false statement, then of course this doesn't work. So the only thing that works is a false statement implying a true statement. So in classical logic, such a paradoxical statement would always be false. But in this case, it is actually not consistent. Classical logic is a formal system that is not consistent because it assigns the truth value false to paradoxical statements, while the paradoxical statements actually should not be assigned either false or true, because they are simply paradoxical. So if in classical logic each statement is assigned true or false, then this is a complete language but not a consistent one. And a consistent one would not be complete because it would not assign true or false to paradoxical statements, and so it would not assign true or false to all of its statements that are in this language. And the second theorem, it is related to the halting problem. So you can't prove either that a program can detect whether it itself terminates or not. Okay, if it terminates, then maybe it will detect this, but not terminating this will simply not work. So this is a bit simplified, a justification for the second incompleteness theorem of Gödel. But as I told you, I wrote about this, and you can find my texts on my website. So if you are interested in this subject, I would recommend reading a bit. So thanks for your attention again. See you.